Hello, hello. Welcome to the warm-up checks for 3.1. 3.1 is about the concept of signed volume. And volume, we're going to use the same word to also describe two-dimensional area as well. First of all, let's look at parallelograms. We know a lot about parallelograms. They're going to be important in linear algebra because, of course, if you have like one vector here and another vector here, and you add them up, you get the third vector at the corner. And if you add them in the other direction, you get the opposite pair of sides. So, yeah, parallelograms are closely related to linear algebra. And to get the area of it, well, like the area of this parallelogram here is the same as the area of the corresponding rectangle that has the same base length and height here. Like you can imagine that if like you had a deck of cards and you like push them over in this direction, it would still be the same size deck of cards, like without removing or adding any cards to it. The area of the side of it is still going to be the same. So, yeah, the area of this rectangle is the same as the area of the parallelogram. Now, before you do exercise 1, we also want to define this thing called the parallelogram determined by A. What we mean by that is if you have like the two columns here, A1 and A2, then like in this case, this is the parallelogram determined by A. Um, and in each of these cases, the two vectors are a little different. We're messing around with the vectors to make a new parallelogram determined by a new matrix. And so we're finding the area of these different parallelograms determined by different pairs of vectors, and also say which ones are linearly independent. So yeah, the answers will show up in a moment, so hopefully you've done them. You have 3 seconds to pause the video. 3, 2, 1. And here are those answers. Now, the first 3 of these are all area 6. And a good way to think about why these are all the same is because they all result in moving the parallelogram in a way that doesn't change its volume. Just like if you have a stack of playing cards and you like sort of push it over to one side, there's still the same area on the side of that stack of playing cards. So these are all 6. Here we're just replacing A2 with A2 minus 1/3 A1, which gives you this vertical vector here. And then after you've messed with that, you can like slide the deck of playing cards. Well, I guess now the cards are like facing a different way, but that's okay because we're just like taking this vector and sliding it down until we get down here. And so we're not changing the fact that one side is a distance of 3 away from the other side because we're moving that side parallel to the other side. So this horizontal distance stays the same. But if you take one side like this and multiply it by 1/2, that's going to make your height half as much as it was. Now the height is 1, whereas it was 2 before. So this is likewise scaling the size of the area of the whole parallelogram by 1/2. Now, here are two linear combinations of E1 and E2. the area of this one is 1. And yeah, these are linearly independent. All of these are linearly independent except for D, where the two vectors lie on the same line through the origin. And if that is true, that gives you a volume of 0. The parallelogram is just a line segment, and so the area is 0. So those are the warm-ups. We'll talk more about what the meaning of all of this is in the next video. I will see you then.